Hey everyone, this, believe it or not, is the last video in this unit of dynamics. We've finally made it. Very exciting. In this video, we're going to be talking about the big deal, which is, of course, word problems. Everyone hates them, and word problems are kind of the big portion of this unit because at the end of the day, all the stuff we've been learning has been to get us to this point where we can solve word problems. And they can be really confusing, but word problems are a really important component of dynamics because it's, again, what we've been working up to. And I'm going to divide this video into two sort of sections. The first sections are going to be general steps for how to solve the vast majority of dynamics word problems. And the second section is going to be a couple different tips and tricks, sort of, to help you along your way. And I'm hoping that this will be more useful than me actually going through existing problems, because this kind of applies generally, and I'll hopefully help you, because our test is coming up, actually do test questions in a kind of systematic way, because at the end of the day, if you end up being very super confused in test questions, at the very least you'll know kind of the steps to go through to get something. Even if it's not a full answer, you can really get those part marks. Okay, we're going to start with talking about the steps. And these are kind of the general steps that I go through personally, mentally, when I sit down to solve a word problem. And you might have different steps, or maybe the same steps in a different order. That's fine. This is purely a guideline for how I recommend you approach word problems, especially in dynamics. The very first thing you do when you sit down is obviously read the question. So, I mean, this is kind of, we should know this. Reading the question is important because there might be some tricky things hidden in the question that unless you really read it in detail, you won't fully understand. And it's important to really get your grasp of the question. One small tip here is sometimes in Google Forms, the question, which is multi-part, might have a part A, a B, a C, a D, is just like kind of all strewn like this across the title. And, you know, there might be an A here and a B here. It's kind of impossible to read. One thing that helps me sometimes is to copy and paste the content of the question into a Google Doc and format it properly, where you have kind of the intro to the question, and then an A, and then a B, which is how you would see it in a textbook or in a written test that's like on paper. And this can really help you not miss kind of a section of the question, which I've definitely done in this weird Google form format. Once you've read the question, the next most important thing, in my opinion, is identifying the type of system that you're dealing with. Is it a friction system or is it a non-friction system? And there's a couple ways you can do this. Basically, once you read the question, usually it's pretty obvious. If they're mentioning things like coefficients of friction, if they're telling you values of friction in any way, or even simply saying that there is friction, or, of course, if they're literally asking you to solve for mu k or mu s, which are the friction variables, then you know that this is a friction question. If, on the other hand, they explicitly mention words such as frictionless, or they say that friction is negligible, which means that it doesn't factor in negligible, or perhaps in some cases, if they just don't mention friction at all, you know that it's probably a non-friction system. On our specific test that we are doing, there is precisely one friction question and one non-friction question. So when you read the entire test, look over it, make sure you know which of the questions involves friction and which doesn't. Okay. Now, the test is likely going to be broken down into a number of sections. Usually part A, part B, part C, or something along those lines. What you want to do is go through each of those sections, and you're going to do a couple things. The first thing you want to do for each section, you want to start by determining the method you're going to use. And there are two methods, which just get referred to as method 1 and method 2. So method 1 is kind of the typical thing we would do, which we would create a free body diagram for each object in the system. For example, if there was a system which was like 2 boxes connected by a rope, you would do a free body diagram for this box and a free body diagram for that box and start solving the question. Method 2, on the other hand, says, no, we're actually going to treat this entire thing like one box, and we're just going to solve for that. Method 2 deals with the entire system as one free body. Method 1 deals with multiple components as different free bodies. And there's reasons you might want to use each one. Method 1 works better for if you need to find internal forces or multiple forces. And by internal, I mean forces which are inside between here. For instance, if you needed to figure out the tension of this rope here, you could not use method 2 because method 2 would ignore that. You need to figure out this internal force, so you would need to use method 1. Method 2 comes into play in certain things if you are dealing with stuff like finding external forces. So, if there's an overall force normal here because this entire thing is sitting on something, I don't know, I'm making stuff up here, but you might use method 2 because you could just abstract this whole thing into one box. Another common reason to use method 2 is finding acceleration of a system or of an object. That's usually a good reason to use this single free body diagram approach. If you're really in doubt and you have no idea which one to use, take the tiny little bit of time to make a free body diagram for the entire system. That's method 2. And then you'll immediately see if that's not going to help you at all, in which case you need to move on to method 1. But you've wasted so much less time than if you try and make a free body diagram for everything, like method 1, only to find out that you could have just made do with one whole free body diagram. Okay, so you found the method. The next thing you need to do is set the direction of the system. And when I say set the direction, I mean you draw one of those arrows which looks like this with a plus sign somewhere on the system. Now, how do you set the direction? Well, sometimes it's super easy. In kind of normal systems where there's just like items on a ground or something, you'll typically start by setting a vertical direction that is up, which is usually the correct approach. And then depending on which way the thing is moving, for instance, let's say this is a train and the locomotive is here, so you're moving here, you may as well make this direction positive. If on the other hand you were moving this way, you would make this direction positive. If you're dealing with vertical motion where things are just falling downward, you might want to make down positive. In general, follow the motion of the system. And this is even more true if you have a complicated system like this sort of thing with a pulley and another system. The correct approach here is actually to make this direction, this whole direction positive. So this way and this way. And sometimes you can get into really crazy situations where you might have boxes going like this. Here's a pulley, here's another pulley, here's a box and a box. And the correct approach here might be to make all 3 directions positive. And you're like, okay, yes, up and down are positive. Thank you. That's so helpful. But it really is, because when you're solving for this box, the direction it is moving is this way. And so it makes sense that that direction be positive. But this box, the direction it's moving is this way, and it makes sense that that be positive and this be that positive. The rule of thumb here always is, in general, set the direction of the motion for every different thing to be positive. So you should always be, in most cases, dealing with positive in the direction of the movement. So the first question in most things is really, which direction, if any, is it moving? Okay. After that, the next step is to draw free body diagrams. And you've just determined, when you figured out the method, which free body diagrams you're drawing. If you're dealing with method 2, well, simple. You just need a free body diagram for the entire system. So this entire train car, for instance, might get a free body diagram. If you're dealing with method 1, you now have to draw free body diagrams for multiple things, and the question becomes, which things do you draw free body diagrams for? And the thing here is really to just look at, what is the question asking you? Usually it's asking you about a force at a specific point. For example, back to this example here, I'll highlight it. The question might be like, oh, what's the tension of this rope here, rope A, which is this, thing here. And so clearly the free body diagrams which you need is a free body diagram for this and for this. So in this case, you need to draw all the free body diagrams, and you know that. However, a question like this might concern you by saying, oh, you need just this string. You know, maybe it doesn't care about this string, just that one. Find this. Well, then this free body diagram is not very helpful for that section of the question. You can just draw a free body diagram for this and this because the force involved goes between them. And that's the general rule of thumb. If the force involves a box and you know you're using method 1, draw a free body diagram for it. It's also worth mentioning that in general, you can't draw too many free body diagrams. If you just are looking at a question, you're like, I have absolutely no idea what to do, draw all the free body diagrams, every object in the question and the whole system, and then look at what you're doing. After free body diagrams, you need net force equations. Now, I say you need. There are situations in which this is not the correct next step, but for the vast majority of times, the correct thing to do now is net force equations. When I say net force equations, I'm referring to equations which look like this, where you have F net in X and in Y, and it says that they equal, you know, in the X you might have an active force minus the kinetic friction force, things like this, you know, your force normal minus your gravitational force. Net force equations are the next natural step because they tell you, what do I know? What are the knowns? You know, then maybe you could fill in the gravitational force because you know it, for instance. Maybe the normal force was given in the question or the active force. And they also tell you what you don't know so that you can figure out what I need to find in order to solve the problem ultimately. Sometimes you actually need the net force. Sometimes you don't. But you can always remember that the net force also equals mass times acceleration. And I'm going to get to this in a little more. We remember that net force equals mass times acceleration, obviously. And so the net forces that we care about, which is, I'm going to be honest, usually, but not always the x, equals mass times acceleration for that body, which can be helpful. Even if you're ignoring this portion, this is still often an important part of solving the problem. Unfortunately, the last section of this is probably the least useful, and that is you need to solve the problem, which seems like just some fantastic advice. But what this really means now is looking at all the information you have. You have free body diagrams, you have net force equations, maybe they're even equaling mass times acceleration. You know for that section what you need to find, whether it's acceleration, whether it's friction coefficients, whether it's one of the different forces. And from that, it's now time to get to that point using math. Sub in the values you know, rearrange equations, all with the goal of trying to get to the point where you have a value. And you want to proceed, there's different ways to do this. You know, you can go section by section, which is usually what I do, and go through these steps and then solve. But you could also go through all the sections, just do the preparation up to here, and then solve afterwards once you know all the information. Our test will have 2 questions, like I said, a friction and a non-friction, which will have a part A and a part B each. And so this will probably be 2 questions. Maybe it's asking you for acceleration and then for tension. Maybe it's asking you what's the active force, what's the friction coefficient. These are the kinds of questions you may be asked, but they're pretty straightforward with a little bit of math. Okay. This kind of describes, you know, how I approach this sort of thing. You read the question, determine friction versus non-friction. Then for each section, you go through the method, find the direction, draw free body diagrams, make net force equations, and then solve. Finally, because we're done the steps, I'm going to just share some random sorts of tips that I found helpful. First things first, and I already mentioned this before, but I'm just going to mention it again for the sake of just collecting all the tips here. And that is, if you have a bunch of objects and you're doing method 1, but you just need the force that's between 2 of them, you can sometimes ignore the other ones, but more often what I'm going to do here is you combine the rest of them into one body, and I'm going to explain this. Let's say we have a train, and there's a bunch of, train cars. I know high quality drawing, I try. And they're all connected by what are effectively tension forces. Well, the question's probably not going to ask you what's the tension force on every single car. It's more likely going to be like, what's the tension of, this string? And your first thing is like, oh my god, do I need to draw free body diagrams for each of these and go through them? And no, you don't. What you're better off doing is creating two bodies here. A body which is all of this, and a body which is all of this. And in between these bodies is the force. When you abstract this away, the force is here. And these two bodies will have the mass that's a combination of these, and you ignore all the internal forces and only deal with external forces. And because of that, this simplifies the problem. If this train car had 200 cars on it, you don't need to actually draw the free body diagrams and calculate net forces for every one of those 200 cars. You just need to calculate, from the first car to the 150th car, and then from there on, and then you can find the force of tension at that 150th to 151st car. That's one tip. Next tip, which is more of just a thing to remember, Newton's laws of motion. I can't say it enough. If you don't know Newton's laws of motion, you will not be able to solve a lot of things. Newton's laws. The first one's good to know, inertia and how it works, but it's not really a formula you can actually apply. The other two laws are very important. That is that F net equals mass times acceleration, which is Newton's second law, and that the force of A on B equals the reverse of the force of B on A, which is Newton's third law. These are both very important for solving word problems. The first one relates acceleration, which is a kinematics concept, with mass and net force, which are dynamics concepts, which is really important. If a question gives you acceleration but not a whole lot else, you can probably plug it into here. Similarly, if you need to find acceleration, which is often what gets asked, you can figure out forces, you'll usually have the math, and you can get your acceleration. Newton's third law is important when you're dealing with multiple bodies, and it's really just something to remember. If there's two bodies here and they're connected, and you're pulling on this body, or this body's pushing onto here, that's a better example. If this body's pushing onto here, don't forget that this body also has to have a reaction force. All too often, people forget about the reaction forces for their actions, which causes a whole lot of problems when you then try and solve the problem. Remember Newton's laws. In the same vein as Newton's laws, remember this really useful equation right here, which is that the force of gravity is equal to the mass of the object times acceleration due to gravity. And we know that acceleration due to gravity is 9.8 meters per second squared down in, probably every question you're going to be doing. If the question opens with "we're on the moon," then don't use that. But otherwise, this is probably the value. And this equation is very useful because any of those net force formulas, which you have like F net of y is going to equal, the normal force minus the gravitational force. And you're like, well, how do I know the gravitational force? You do know it. You can always replace Fg with mass g. And you know g, and you probably know the mass because it usually tells you in the question. This is very helpful. Saves you a lot of time. Secondly, remember how to expand friction forces. I'm doing this with kinetic. Static is the exact same thing. Remember that this almost always expands to this. And why does this expand to this? Well, the reason is because this thing here, we can remember that the formula for kinetic friction and static friction, but this one is for kinetic, is this special friction coefficient times the normal force. Right? We remember this. This is the normal force. And so we go here and we're like, okay, I need to figure out the normal force. So we say, well, the net forces of whatever object we're dealing with is usually a normal force minus a gravitational force. Again, not always, but the vast majority of objects which are kind of sitting on something, normal force, gravitational force. And when you have this arrangement here, you'll realize that you can basically rearrange this, because net force has to be 0 because, if the box is on the table, the box isn't moving. And when you have 0 equaling this, that means that Fn is equaling negative f of g, which is just going to be fg in terms of magnitude. Like, they're going to be going opposite directions, but it's the same number. Because Fn gets moved over here, and it becomes negative, so you'd have negative Fn equals negative Fg, which is just Fn Fg. And when you know this, you can realize that this is mg, because we just talked about that over here. And so you can put this value back in here, and you end up with the fact that in a lot of cases, don't just assume this, do this work, but just keep it in the back of your mind that in a lot of cases, you're going to end up with what I remember, even though this is not really right, as UMG. It's technically this, but UMG helps me remember. And that is usually the correct way to get friction, both kinetic and static, if you replace these K's with S's. And because the deal is you're going to get these net force equations, and you're going to need to replace these just variables which represent forces with something a little more specific. For instance, the fact that the force of gravity is mass times acceleration due to gravity, or the fact that friction is mass times acceleration due to gravity times the friction coefficient. In the end, all of these are tips and steps that really are just here to help you with word problems the best that I can. At the end of the day, my final tip is basically this. Go through this, have a routine for the question, read them, go through the steps, use these tips, memorize them to the best of your ability. Some of them you might even be able to put on your organizer, which you could literally have there to look at. And with all that, look at the question and just really try your best to go through it systematically and figure out things you can figure out. If you are super confused, have no idea what to do, just figure out free body diagrams, net force equations. You can always figure those out, and it'll get you somewhere. And even if you then give up on the question, you've at least gotten the bare minimum part marks. Like, you've started that question. You understand the system. You might not understand how to solve the system, but you understand the system. Also, if you get very close, or at least most of the way through a question, but you start to run out of time, which is a real issue, I suggest actually writing out what you would have done. Really going there and being like, Miss or Mr., I ran out of time, but then I would have solved for this value, subbed this into this, done this, and that would have given me my value. And that at least tells the teacher that you have a concept of what you were supposed to do. You just didn't have enough time. And that's really better than nothing, and will again get you more of those part marks. In the end, taking tests, doing word problems is an acquired skill. Physics tests, physics word problems are difficult, but hopefully with the help of these steps and these tips, you'll be okay and be successful. Good luck to everyone, and thanks for watching.